Hello everyone, and welcome to our talk about physical properties and intermolecular forces. So this is something that once you learn it will apply to a lot of different systems. So we're only going to talk about it for one day in lecture, but then we're actually going to use systems that have to do with physical properties or intermolecular forces a whole bunch in the lab. So you'll get to see a lot more examples there. We'll probably bring up some biological examples. So expect to see more of this, especially outside lecture. So we're going to start off with just a quick conversation or reminder from Gen Chem about intermolecular forces, and then we're going to move on to physical properties. The physical properties that we'll focus on will be boiling point and melting point. Those have the same trends, those go together, and then we'll also talk about solubility. So first, just as a reminder, whenever we say intermolecular forces, usually I say IMF, what we mean are forces between two or more molecules. Generally, these are the same molecule if you're talking about physical properties, like they would be two molecules of water or two molecules of methane, or they could be, in the case of solubility, in between the solvent and whatever's being dissolved. So it just depends on the system which ones we're talking about. It's important to notice that we're saying intermolecular forces. There's also something called intramolecular forces, and the difference is whether it's inside the molecule or between different molecules. Intra is like intramural sports, that's within the school. An intramolecular force would be like the bond strength, and that's definitely not what we're talking about. That's not related to the physical properties at all. So when we're thinking about the intermolecular forces, there's four main types that you probably have heard about. So pause the video and think for just a second about what are the intermolecular forces that you've heard of. So my guess would be the one that's the most easy to remember for everyone is hydrogen bonding, so I'll write that one down. That's actually not the strongest one, but that's the one that people will remember the best. So underneath hydrogen bonding, we would have dipole-dipole. That's whenever you have two polar molecules next to each other. And then if you have nonpolar molecules, that would be dispersion forces, or some people call it London dispersion forces, or you might call it van der Waals. Van der Waals is what I call it, so if you ever see that, that's what I think of it as. But all those things are the same thing. The one that sometimes people forget is ionic or ion-ion. That's like whenever you have a charge. So we'll still need to know about ion-ion interactions, but we just won't see them quite as much in this class. So let's talk about how we would recognize each of these different intermolecular forces. So the first one is ion-ion. For this one, they have to be ions, like it says. So that means we're going to have compounds that either have a metal, usually with a nonmetal, or a charge, so like a negative charge or a positive charge. So a classic example would be sodium chloride. So you can see there's a metal there, right? That's the sodium. So that's how I know that it's going to be ion-ion. Now, sometimes it'll just be one half of this. Like if I just said Cl minus, you would know that it was ion-ion because it has a negative charge. So that's the only one that's actually for ionic bonds. Everything else below this, like 2, 3, 4, are for covalent molecules. So the strongest of the covalent molecules are hydrogen bond. So if you think of water, that's the classic example. Basically what you have to have a hydrogen bond is you have to have something bonded with hydrogen that's super electronegative. So like we're going to put Z just meaning generic. The three things it could be a fluorine, it could be an oxygen, or it could be a nitrogen. So like an NH bond, an OH bond, or an HF bond. Those are the three that can be hydrogen bonding. So if you see that type of bond, it's hydrogen bonding. This is a special case of the next one, which is called dipole-dipole. Dipole-dipole just means that the molecule is polar. So it has to have polar bond for that to be the case. So as you can see, I put an example here as CO. CO would be polar because it has two different elements with different electronegativities, and there's nothing to balance that out, so that's going to have an overall dipole. So there's some stuff in your book about that you can review, but that's what you're looking is polar bonds and a dipole. And then if it doesn't have polar bonds and any of these other ones, then that means it's nonpolar, and that's generally going to be dispersion forces. So dispersion are the weakest forces if you count them like per atom. An example of this would be like H2. They're the weakest forces, but also it depends on how big the molecule is, how much the dispersion force is that you have. So we'll talk about that as well. So generally, people usually feel pretty good about 1 and 2. Sometimes there's a problem between 3 and 4. So let's talk about those for just another minute. The main issue trying to distinguish between 3 and 4 is that you can't always tell just by looking at the elements. You have to actually know something about what it looks like in 3D space. So the first thing you're going to do is get the Lewis dot structure, and then from that you can get the Vesper structure, so we've already talked about that. And then what you're looking for is two things. The first thing is a polar bond. Does it have polar bonds? The next thing is, does it have polar shapes? A polar bond, as you know from the readings, is just any bond that has elements with two different electronegativities. So as long as they don't have the same electronegativity and they're different elements, nonmetals, then it should be a polar bond. There is an exception to this. Carbon and hydrogen, the electronegativity just happens coincidentally to be really similar, so those are not considered polar bonds. For a polar shape, you have to have the structure usually, and according to most books, you would do some sort of vector analysis on it. That's a little complicated. Some people love that, some people don't. So just in case you're a not vector person, I'll give you a tip. Basically, what you can do for the polar shapes is look at two things. The first thing is there a lone pair on the central atom? If there's a lone pair on the central atom, it's generally going to be a polar shape. Now, this only really works for organic chemistry where we only go up to tetrahedral. If you were going to go to like bipyramidal or anything like octahedral, then that's not true. But for all the cases we're going to see, it's going to work. So if there's a lone pair in organic on the central atom, then that means that that is already going to be uneven, and therefore there's going to be a polar shape. The other thing is if you have different elements around the outside. So the central atom, not looking at that, the ones attached to the central atom, if they're different, then you know that there's going to be a polar shape, because that means they're not going to be pulling equally. So looking at these tips, we can see that for number 3, the example CO, does it have a polar bond? Yes, it has a polar bond because CO are different elements. So they're different electronegativities. Then does it have a polar shape? Yes, because looking at this, there's a lone pair on the central atom, assuming it's carbon. It could be oxygen, actually. In this case, it wouldn't matter. So yes, there's a polar shape also. For the number 4, does it have a polar bond? No, because it's got hydrogen, and that's the same element, right? Hydrogen and hydrogen. So if it doesn't have polar bonds, it can't be polar at all, so we just stop. If it had a polar bond, we would then check and see if it was the polar shape, and then we'd do the step 2 here, but this one doesn't have polar bonds, so we can just stop. To be a polar molecule, it has to have both a polar bond and a polar shape. So if we see both of those things, then it will be dipole-dipole. If we don't have both of them, and it's not the other two, then it's going to be dispersion, aka van der Waals. So the first thing we're going to want to be able to do to move on is to identify the strongest intermolecular force for a certain molecule. So I say strongest because actually if you have, say, hydrogen bonding, then every molecule that has hydrogen bonding also has all the forces that are weaker. So it would also have dipole-dipole, and it would also have dispersion forces. So the strongest one for that molecule would be hydrogen bonding, but then it would also have those other things. So looking at the molecules, we can sort of go through these. We're not going to go through every single one right now. The answers will be posted on a different activity, but you can see some of these you can identify without even looking at the Lewis dot structures. So pause the video and check which ones do you think you can figure out without the Lewis dot structures or drawing anything. All right, so hopefully you got these. So looking at the examples in blue, just by looking, I can tell that there are 3 that are ionic. So which 3 would those be? Right, it's going to be anything with a metal and anything with a charge. So it'll be the calcium bromide, the sulfate ion, and the magnesium nitrate. So I also know that there's going to be 2 that are dispersion / van der Waals forces. So these are ones that don't have polar bonds in this example. So what are the 2 that don't have polar bonds? Right, it's fluorine, so F2, and this CH3 in the bottom right. That doesn't have polar bonds because we said carbon-hydrogen bonds are not polar. So then moving right along, one of these has hydrogen bonding, right? That's going to be the NH3 because NH is a hydrogen bond that you can have. And then the last one is dipole-dipole. So the only one left would be HCl. So HCl is a polar bond because it's 2 different elements and there's nothing else that could possibly balance it out. So we know that's got to be a dipole-dipole. It's not hydrogen bonding because hydrogen bonding has to have hydrogen plus either hydrogen-oxygen bond, hydrogen-nitrogen bond, or hydrogen-fluorine bond. If you're curious about the rest of these, you can either do them and have me check them some other time, or you can check, I'll post the answers in the additional activities. So now what you may be thinking is, why do we care about intermolecular forces? So let's find out. Everybody knows that matter can come in different states. You can have a solid, liquid, or gas. So that means that they can also interchange in between these two based on the energy and what the molecules are doing. So in a solid, the molecules are very close together and organized. They don't have enough room to really move, so they just kind of wiggle and they stay together very tightly. In a liquid, they can flow around each other. In a gas, they can actually be completely free and there's a lot of space between them and they bounce around. So what is holding those things together is intermolecular forces. So in a solid, the forces are very strong and they're holding it very tightly so that they won't wiggle apart. In the liquid, they're a little bit looser, so there's a little bit more freedom to sort of slide around each other. But they still want to be touching each other, they just don't have a particular one they have to be stuck to. They can slide around. With a gas, they obviously don't like each other very much. The intermolecular forces must be weak because they don't want to stay together at all and they're just flying apart with lots of empty space. So we can use the intermolecular force argument to figure out how likely something is going to want to be a gas or a liquid or a solid at a certain temperature. For the physical properties that we're going to talk about, we're mainly going to focus on boiling point and melting point, and then we'll talk a little bit about solubility. The important thing is that all these things are based on intermolecular forces. So let's talk about what stronger intermolecular forces actually means. Imagine I have two liquids. In one of them, the forces are really strong, and in the other one, the forces are weaker. So if that happens, I want to break them apart to get them to boil, right? So if I want something to boil, I have to increase the energy outside the molecules, like heating it up, like boiling it on a hot plate, for example. And as I keep heating it, eventually the energy that's outside to make it want to move around, the kinetic energy, is enough to make it overwhelm the forces that are holding it to keep them close together. So if I have something that has stronger intermolecular forces, would that mean the boiling point is higher or lower? Right, it's going to mean it's higher. It's going to mean it's harder to make it come apart because the forces are so strong. I have to heat it even more to overcome those forces. So the boiling point should be higher. A classic high boiling point in our world, in organic, is water. Water boils at 100 degrees Celsius, which is 212 degrees Fahrenheit. That's actually pretty hot for the organic lab. Lots of the other solvents boil much, much lower. The reason for that would be water has hydrogen bonding, whereas most of the organic solvents have more dispersion or dipole-dipole forces, which are weaker than the hydrogen bonding. Using that same logic, what do we think about the melting point? If I have two solids and one has stronger intermolecular forces, is it going to be easier or harder to break them apart to melt it? Right? It would actually be harder to break it apart if it's stronger forces. So again, you're going to have to heat it up more to make that happen. So the melting point would be higher. So knowing that, let's look at the second type of problem that I'd ask you to do. I might ask you to rank molecules in order of boiling or melting point. The trend would be the same for melting or boiling. It just depends on if they're usually liquids or solids that I would choose my wording there. So there's two things we're going to look at. The first thing we're going to look at is what's the strongest intermolecular force for those molecules. If they're similar sizes and the stronger intermolecular forces are different, then we're going to assume that the strongest force will win. So if I look at sodium chloride versus water, which one would be a stronger intermolecular force? Pause the video and decide. Right, it's going to be the sodium chloride because that's ionic, which is more powerful than hydrogen bonding. So that's going to work a lot of the time, but sometimes there might be other situations that that's not going to work. So if there's a tie, they both have the same strongest intermolecular, then I'm going to look at the tiebreakers. So basically, I'll show you some of these tiebreakers in the next video. There's also some exceptions. So if you have molecules that are very different in size, then van der Waals forces take over, dispersion forces. So the more surface area you have, the more dispersion forces you have. So if they're totally different sizes, then that means that the van der Waals will win, and it could be a higher boiling point just because of that. So we'll end here for this video. Be sure to check out the next video, which will talk about the tiebreakers that we mentioned earlier. Thanks!